All right, so this video is about entropy. Entropy is a fancy term for disorder or chaos. All right, in your reading that you were supposed to have done for today's class, which I think I forgot to mention in the email, but it was on your agenda. So you're supposed to read the beginning of chapter 17. So if you haven't done that, please make sure you go back and read that and fill in your guided notes. So entropy is, like I said, randomness, disorder, chaos. Think about your room at home. What happens to it over time? It gets messy, right? Unless you do something to keep it nice and ordered, it's going to naturally get messy over time. Okay, maybe you're one of those people that you always keep your room really, really nice and you don't have to think about it being kept tidy. It just naturally happens because you've been drilled to keep it tidy. Think about this room, the room we're sitting in right now. What happens to these desks over time? They start to move around. As people are using them, as different classes come in, they start to get moved around. And what ends up happening, at least with these two groups, you guys end up getting pushed forward, and then these ones end up getting closer together, and then I periodically have to go through and shuffle and put them back to where they're supposed to be so that everyone can sit and hopefully see the board nicely, okay? That's entropy. That is the increase of entropy. All right, this first problem, number 26, is talking about is entropy increasing or decreasing with each of these processes? And then we're going to do some math with it in number 27. Okay, so in number 26, the first example is ice melting at 0 degrees Celsius. We're not going to even worry about the math with this. We'll see the math with it later. But for right now, let's just talk about conceptually. Is the disorder of the particles increasing or decreasing, or is it staying the same? Okay, Dare says it's increasing. Why? That's a great way to describe it. So as ice melts, as it goes from a solid to a liquid, particles are moving further and further apart, and they're moving more. Increase of temperature will also increase entropy. So basically, the more movement you have of the particles, the more randomness or disorder or chaos that they have. So yes, solid to liquid, we have an increase in entropy. The particles, like we said, are moving faster. And that's more disorder, more chaos. The symbol that we give entropy, so enthalpy has to do with heat. What was its symbol? No, its symbol, not its sign. Delta H. Enthalpy was delta H. Entropy is delta S. Okay, don't ask me where the S comes from. I don't know. I know it comes from somewhere. It's not something that you need to worry about. It's not going to be a question. What's the S stand for in entropy? Maybe it's named after someone. I don't know. So this delta S, what would the sign be if our delta S is increasing? Positive. If our entropy is increasing, we have a positive delta S. All right. A precipitate forms in aqueous solution. What do we think there? What's happening to entropy? What's happening to the randomness of the particles? This one's decreasing, okay? And the reason why is, in addition to the movement of the particles, entropy is also looked at in terms of the types of particle arrangements we can have. It's something called a microstate. When you go in a reaction of two aqueous solutions, there's a lot of different possible arrangements of those particles because they're all free-flowing. They're all moving ions. Once you take some of them and force them to make a precipitate, they get locked up. It's kind of like being landlocked. They then can't go anywhere. All right, so it's decreasing the possible microstates. So formation of a precipitate is a decreasing in entropy, so it'd be a negative delta S. So the reason, let me write down the reason for this is we have less randomness in the particle arrangements. Okay. All right, what about a solid dissolving in water? That is increasing. We're going from a solid to an aqueous. So kind of like when I was talking about before with B, when we have two aqueous solutions, all of those particles are free moving. When something's in solid form, it gets locked up. So going from a solid dissolving, that is an increase of entropy. So it'd be a positive delta S. And like I said, now we've increased the randomness in the particle arrangements. My E caught weird. Okay. And then the last one, gas condensing to a liquid, decreasing. Gas to liquid, so that's like the opposite reason why solid to liquid was increasing entropy. Particles are moving faster when we go from solid to liquid. When we go from gas to liquid, the particles have to slow down and you're removing energy. So we have a negative delta S here. So yeah, when you go from solid to liquid, liquid to gas, or solid to gas, when you're like doing those phase changes, that is an increase in entropy. When we do the opposites, it is a decrease in entropy. Yes. Yes, it very well could stay constant. Yeah. It's rare though. It's rare for a chemical reaction to not have a change in entropy. And that's what we're mainly going to be looking at, are chemical reactions. All right, and that's what we're going to see in number 27. Okay. Any other questions on this before I move on? Okay. All right, number 27. So we have this reaction. This is the formation of ammonia from its individual elements. And we're told it's carried out at 100 degrees Celsius. The temperature is important for something later, and we'll talk about that in just a little bit. But let's take a moment to talk about the reaction itself. Let's predict the sign of our change in entropy before we actually calculate it. Let's look at the reaction. What do you think the sign, thinking back to like the conceptual stuff we just talked about, what's the sign of our change in entropy? Why do you think it's positive?
Because it's like going to be fewer particles, so it'll be more random. Like there's, not that.
So I get what you're saying, that you're thinking that there's fewer particles, so it'd be more random because there's less going on, right? But because we have fewer particles, we have less microstates. So we're actually, when you're going from multiple things down to one, that's a decrease in entropy, okay? That's a decrease in disorder. So the prediction here, we should see a negative delta S, okay? Synthesis reactions are always going to be decreasing the entropy because you're going from multiple things down to one. Decomposition reactions would be the opposite, going from one thing breaking down into multiples, okay? Think about, and then double replacement and single replacement really depends on the coefficients on the substances and the states of matter, okay? That really just kind of depends on what's going on. Combustion's typically going to be an increase in entropy as well. Okay. All right, so calculations. Letter A is asking for the change in the entropy of the system, which is our reaction, okay? So our reaction. This we're going to calculate using Big Mama version 2. Okay, so Big Mama version 1 is what you watched in the video on your snow day. The delta H of reaction equals the sum of the delta H of formations of the products minus the sum of the delta H of formations of the reactants. That formula is on your formula sheet. Big Mama version 2, it's the same formula, just instead of delta H, it's going to be delta S, and that one is also on your formula sheet. Okay, so this is what we're going to be calculating. So delta S of reaction is going to be equal to the sum of the delta S of products minus the sum of the delta S of reactants. Okay, and the values for the products and reactants are found in tables. I have them for you so you don't have to look them up, but for your homework, you will need to use your textbook to look up the values. If you look at the back of the textbook, there's an appendix that has all the thermodynamic data for delta H, delta G, and delta S. We'll do delta G in a couple classes. Okay, so with this, so delta S reaction equals, so our products, remember you take the moles from the coefficient and multiply by the value. I've looked up the value. NH3 is 193, and the units there are joules per mole Kelvin. Delta H and delta G are typically kilojoules per mole. Delta S is joules per mole Kelvin. So just be aware that they are slightly different units. Minus the stuff on the reactant side. So we have one NH2, or sorry, we have one N2. N2 has a delta S of 192. I'm not going to worry about the units here because they are all the same. Plus 3 H2s, which is 131. From the video that you should have watched prior to this class, N2 and H2 would have had delta H values of 0 because they're individual elements in their standard state of matter. Delta S, typically none of those values are going to be 0. They're always going to have an entropy value. All right, so when you do the math here, go ahead. And what do we get? Who's going to get it first? You're close. You're closer. Further away. Oh, what? Negative 199. And that is delta S of the reaction, or the system. Okay, delta S of reaction, or you can say delta S system. Okay, cis, yes. All right. So calculate the change in the entropy of the surroundings. Well, that is not necessarily, so the entropy of the system and the surroundings are not going to be same magnitude, opposite sign, because there's other stuff going on. So delta S of the surroundings, this was in the reading in the beginning of chapter 17. Delta S of the surroundings is delta H of the system, or the reaction, divided by the temperature in Kelvin, and then there's a negative sign in front of that. So, FYI, a big T, a capital T, typically means temperature in Kelvin. A lowercase t is used for temperature in Celsius or time. Okay, but if you ever see a big T, that's always going to be referring to temperature in Kelvin. Okay, so in order to do this, we have to calculate the delta H of the system and then divide it by the temperature in Kelvin and then negative it. Okay, so to calculate delta H of the system, that's going to be Big Mama version 1. Like doing the delta H of the products minus the delta H of the reactants. Again, I've already looked up these values for you so that we don't waste time. NH3 is negative 46, and this is all kilojoules per mole, minus 1. N2 and H2, what are their delta H values? 0. Good. Even though I'm writing this, even though we don't need it. So it's really just 2 times negative 46 minus 0. So 2 times negative 46 is negative 92. And again, these are kilojoules per mole, not joules per mole. And that's our delta H of system. And now we plug that in here for delta S of the surroundings. So negative 92 kilojoules per mole over, what's our temperature in Kelvin? What is it? 373. Because we have 100 degrees Celsius, so you add 273 to it. And we're going to imagine that that 100 degrees Celsius has 3 sig figs. All right, so when you do that math, what do you get? What do you get? 0.25, yes, 0.25, and our units are kilojoules per Kelvin mole. And that is delta S of our surroundings. All right. Oh, and I meant to say this before. In A, our calculated delta S of the system matched our prediction. It was negative like we had anticipated. All right, and then for C, we're going to calculate the change in entropy of the universe. Delta S of the universe equals delta S of the system plus delta S of the surroundings. The universe, the entropy of the universe, one of the laws of thermodynamics is the entropy of the universe is always increasing. So we should have a positive value here. Hopefully we do. Now, why can we not just add system and surrounding right now? What? Because of the units. Notice we had kilojoules per Kelvin mole for the delta S of surroundings and only joules per mole Kelvin or Kelvin mole for the system. So you have to get them to the same unit. I don't care which one you do. I put them both into joules per mole Kelvin. So 0.25 kilojoules per Kelvin mole is the same as 250 joules per Kelvin mole. And you just multiply 5,000 or move the decimal 3 to the left or to the whatever that side is, the right. All right, so delta S of universe, it better be increasing, right? We have negative 199 joules per Kelvin mole for the system plus 250 joules per Kelvin mole for the surroundings. Is that going to be positive? Yup. And what is it? Oh, 51. I thought you were saying 58. And I'm like, you're doing math wrong. So, yep, 51 joules per Kelvin mole is our delta S of the universe. All right, so is this reaction favorable? What does it mean to be favorable? Okay, I'll tell you what it means to be favorable. One of the definitions of favorability, or your textbook uses the word spontaneity or being spontaneous, but we've moved away from, AP Chemistry has moved away from using the word spontaneous or spontaneity because students and people think of, when they hear spontaneous, they think instantaneous, which are not one and the same. Spontaneous means that it just will happen. Instantaneous, it's instantaneous is like it's going to happen really quickly. Favorability, spontaneity has nothing to do with how fast the reaction is going to occur. But that's why we've moved away from spontaneity and into favorability, because people were getting confused, okay? So if this is favorable, then it will be increasing the entropy of the universe. Because if the law of thermodynamics says that the entropy of the universe is increasing, so if a reaction causes an increase in the entropy of the universe, then it is a favorable reaction. So it is, I kind of lied to you here, it is possible to have a negative delta S universe. That just means that the reaction isn't favorable. Does that make sense? And therefore it won't happen if it's not favorable. You have to do things to make it happen. You have to basically manipulate it so that it becomes favorable. One of the easiest ways to do that is to change the temperature. So this is favorable because delta S of the universe is positive. Okay? So that is it for today. Next class, we're gonna run our procedures, and you're gonna calculate and figure out which hand warmer is best. And then in 2 classes, we're going to wrap up with Gibbs free energy.